That's what I'm talking about.
Wait! Okay, now, from the beginning.
All right. Good afternoon, everyone. My name is Mike Acton. I'm principal engineer here at Unity. And today I'm going to be talking about our plans to democratize data-oriented design, and specifically about our data-oriented approach to using component systems, and what that means in practice, walking through some of the examples that are now available that we released this week. So, but first, a little bit about me. I've been focused on being a developer for custom engines and lead for engine development teams on AAA games for a long time. Most recently, I was the engine director at Insomniac Games for about 11 years before coming to Unity. But now, I'm at Unity to bring those sort of AAA lessons to everyone, and to bring that tooling and that performance to all of our Unity games across the board moving forward. Specifically, our mission here is to democratize data-oriented design, which means, as Joachim has pointed out, it's about performance by default. It's about the thing that you do, the thing that you put in by default. You know, your first instinct when you put something in Unity should be a good first-level approximation of the right answer. And it shouldn't be something that you need to rethink or throw away or figure out a better solution for. It should be a reasonable solution, should give you reasonable performance, and you should be able to optimize it after the fact to get even better performance beyond that. So as I said, it should also be optimizable by default. So let's talk about a little bit about what problems we're trying to solve. And for me, that means the problem is getting the clowns out of the car. And this is not just Unity, this is the industry across the board. If you imagine trying to bring performance to this particular car, you have somebody working under the hood on the engine trying to make this car faster. The problem is not the engine as such in this scenario. The problem is that your car is full of clowns. And one of the biggest clowns that we have as an industry, as a programming, and how we teach programming, and how we approach things has been for many decades now an object-oriented approach. And that's one of the things that we really need to rethink from scratch to say this is not and has not been a performant approach to programming. Among many other things, right, in terms of our default approach and how we're taught to program, we need to just get these clowns out and focus on the real problems that we actually need to solve, the real games you actually want to make, and making sure that those things are performant. So the problem is that the default approach that we teach is horrible for performance, full stop, everywhere. Not just at Unity, but across the industry in general. The default approach is also not optimizable. By the time you get to the end of your title, by the time you get to the game, the best you can hope for is sort of hotspot optimization. I'm looking at this specific thing. This is the best I can do is just fix this one thing. But across the board, everywhere, I have this sort of uniform problem that I just don't have time to fix at this point. I'm sort of screwed at the end of the game, right? The default approach also introduces sort of problems and complexities, right? You're adding things to the problem that don't actually exist as part of the problem, as part of your mental model, right? So, you now have to solve not only your original problem, but all these other problems that you added to it, based on abstraction or based on, complexities in interconnected systems or whatever. The default approach actually rarely solves the actual problem that you're trying to solve really well. In fact, the sort of a programmer trap is overgeneralizing, right? You're trying to solve for all problems or trying to be future-proof, and by doing so, right, in your design, you are, in fact, solving no problems well and will continue to solve no problems well for the indefinite future, and you sort of fall into this trap. And we want people to be focused on solving their problem, their specific problem for their specific games as well as possible. So why is what we're doing broadly at Unity right now interesting? So the first part of what we're doing is the sort of job system and scheduler combination. And part of that is that you must fully declare the data that you're using in a particular job. So this is the data that I'm reading, this is the data I'm writing, this is all the data that I need, you're declaring it, right? We also need to declare the read and write permissions on that particular data. What this allows us to do across the board for everything that uses the system is verify correctness. We can tell you whether or not something is working. We can tell you whether or not there's going to be a race condition potentially here. And so it gives you a lot more flexibility in terms of iteration. I want to put this on a job. I want this to go wide. I want all these things to interact. I want all these systems to run on all the cores available for as slow, short latency as possible. And we can verify that that in fact will work. However, we understand that not every case is general, right? We understand that sometimes you have a very specific algorithm that you know is correct, right? You know that there are no race conditions, that there's nothing in which the data is sliced in such a way that two things cannot possibly write over each other in multiple threads, whatever. You know that, we can't know that. So we do allow overrides for those specific special cases. As a sort of second leg to this, to what we're doing, we're also working on the burst compiler, what we call the burst compiler. We know that C# is already familiar to our developers, so we're continuing along this path. We're refocusing on C# and a specific subset that we're calling high-performance C#. A high-performance C# is a reasonable subset of C# that is optimizable, that we can reason about, that you can reason about, and yet still familiar in terms of development. This is not a question of C# versus native code, right? This is not about mono versus native. This is ahead-of-time compilation, right? This is actually just compiling the C# code. And what we can also do in the space is, with a better understanding of sort of the data layouts, with a better understanding of what your data read-write permission are, exactly what data you're reading, so we can give that information to the compiler to produce a much better result. Technically, right now, as of today, we're approximately the same level of simplification as, say, ISPC, if you're familiar with that compiler. But going forward, we expect that to be improved quite significantly. As I said, we're comparable to ISPC today. Our advantage in this context is that we have more context. We know more about the data. We know about aliasing concerns. We know how you're using the data, right? So we can tell the compiler to make particular transformations that no general purpose compiler could possibly do because it simply doesn't have that context. Another aspect of what we're doing is memory containers. So the most important part of memory containers is that there's no garbage collection. That this is something that you're in control over and that reasonably fits well within the system that we're building. So you don't see massive spikes in performance over time because garbage collection, right? We're also providing currently some high-level custom allocators for common use cases like Temp and Temp jobs with lifetime and access rules that you can follow. How we expand upon that for other common use cases that we anticipate is still TBD, but we understand the value and importance of this space. The key here is, as I said, this provides us with good aliasing rules by default, right? This is understood by our compiler. The other aspect, and the thing that I'll concentrate most on today, is ECS. ECS stands for Entity Component System, with an emphasis on the component and de-emphasis on the entity part. So what this allows us to do is have a good default data layout. So if we look at the last sort of 40 years of compiler optimization strategy, right, it's been focused on code transformations, making your code slightly better in terms of transformations. There's an upper limit to that, as we've sort of seen over the progress of those decades. And what we're focused on today is taking that to a different level, right? We're focused on data transformations. We're focused on making sure that we can transform the data in a way that's understood and uses hardware that you're using well. So whether that's from a light mobile device to a heavyweight console, we can lay out the data in such a way that that's going to be much more optimal for that piece of hardware. We can also provide you, by default, through the system with a good transformation pipeline that you're running through the data in an appropriate way, and you have a way to transform the data that makes sense in an appropriate way. And the important aspect to this is it's optimizable. You do this once, even if you do it in a naive way, even if you approach it with sort of naive code that doesn't have this super fancy algorithms or whatever, the fact is that because the data is still laid out well, and because the systems are well contained, you can now take that and optimize it and expect the performance to improve. It is something that you can do later. the course that optimization should take, as opposed to throw everything out because nothing will ever work and we're screwed, right? That's not the course it should take. But I think that really the most important aspect of what we're doing here, and the reason why all of this is going to work, is because we're creating rules. We're creating rules around how we create stuff. We're creating rules around how our content creators are going to create things. These aren't complicated rules, but they're hard rules so that you can get the best performance out of the hardware that you want, whether that's because you want low power or it's because you want maximum content. So one rule is, by default, we're iterating streams of data in order. That's the default. That's how things work. By default, we're focusing on small data in those streams. So streams of small pieces of data, whether it's a single float or a float 3 or 4 or whatever. You must declare, as I said, all your data accesses. This is what I'm reading. This is what I'm writing in this context. You must declare those permissions. And as a part of that high-performance C# subset, we're only working with value types. There's no ref types. There's no garbage collection, the whole thing. So let's dig into some examples, exactly, precisely how they work. So you may have seen this before. Running here on my Mac. So let me give you some quick performance numbers just for context. On this my MacBook here, you can do CPU-side simulation of about 250,000 Boids in about 11 milliseconds. So that's easily 60 frames a second. There's more improvements to this to come. Again, as I said, this is an optimizable process for us. We can now take it and make it better. But as a default position, it's pretty good, right? And it's a reasonably good performant default. And this is where we want to be. But as I said, it's released now, so you can download it and test it on your machine and see how it goes, and you can analyze it. The point is that it's in your hands to look at and see the results of what we're doing. When we show a Boyd example, for instance, this question is inevitable, right? Why are you showing sort of a Boyd example on the CPU and not on GPU, where it seems a better fit, right? And there's a couple of good answers to this. One, it's just an example. In terms of examples, right, examples help you discover issues and patterns and things, and it's worth doing an example. There's also sort of when you're building a system like this, there is actually plenty to learn from what we call embarrassingly parallel problems. There's still a lot for us to learn in that space and a lot for us to demonstrate in that space. So it is important that we have them and not just the sort of complex branchy problems as well. And it's also a good way to translate, for you to translate something that's already familiar, that you're already familiar with in this space, right? If you've already done sort of Boids on the GPU or on some other platform or whatever, you can see how that maps to what we're doing. So it gives you a way to translate that. And honestly, finding the right examples is itself a hard problem. So, it's always a struggle to find what's the right example that's not so complicated that it's sort of impenetrable, but not so simple that it's trivial. So I'm 100% open to whatever suggestions you have as our users to say, this is what I would like to see. This would demonstrate to me that this is really valuable. And please jump on our forums and let us know what those things would look like. Just to show you sort of what the profiler looks like, this is our job timeline view. This is a frame in this particular example. This is running 25,000 Boids in this particular example. Comes out to approximately a millisecond of job time here. And you can see it's sort of organized into phases. So you can sort of visually see the phases that are going on. So here we have, I'll go through these phases in detail as we walk through the examples. We have sort of hash positions phase, and a merge cells phase, and a steering phase, and a move forward phase, and a final transformation system phase. So you can kind of visually see the phases of the various component systems doing their work over time, and very wide across whatever CPUs and threads you may actually have. So for profiling, just a couple of tips. If you're digging into this yourself and you're trying to replicate our results, you want to make sure you disable safety checks and the jobs debugger, because all of that verification of correctness actually takes time and injects gaps into the scheduling. And your goal when you're looking at a profile, so if you're building your own stuff, you want your goal here as a first approximation is to minimize those gaps in scheduling. You saw that schedule is packed tightly against each other. That's the kind of thing that you want to actually see in your game. Before we really dig into the container, I want to make one specific point. An entity is not a container. It's not like a game object in that way. And I will talk a little bit today about why that's true. But before I talk about an entity, I need to talk about what components are. From our point of view, components are essentially parallel streams of data, and they should be treated as such. They're in fact, blocks of memory organized into 64K chunks, none of which is opaque. Like we can demonstrate to you and show you, and you should have an understanding of how that data is organized. But effectively, they're parallel streams. They're grouped by what we call archetype, and archetype is sort of a grouping of components that happen to be used together in a particular context. An entity is nothing more than a lookup index or an ID into those parallel streams. That's literally all it is. So you can think about it as a database key, if you'd like, something like that. But it is literally just a lookup index. So in this particular Boyd's example, let's look at sort of how things are laid out. I've shortened the names of these components to fit on a slide. So we have position component, a heading component, a matrix component, speed component, move forward component, and a void component. That's what this particular sample is made out of. So the systems that go into running this example are MoveForwardSystem, BoldSystem, and TransformSystem. So the MoveForwardSystem generally is designed to do exactly what it says. It takes a heading and a position and moves it forward by the heading over your speed for a particular time frame, delta time frame block. So the MoveForwardSystem is completely independent and designed to move forward whatever it is it's attached to. The BoldSystem is designed to change the heading component. That's all it does. It just changes the heading and relies on the MoveForwardSystem to move all the Boyds forward. So Boyd is just a system to change heading. Another system can be changing heading, however mix and match you want to do there. But its entire purpose is just to change the heading component value. TransformSystem takes the heading component and the position component and creates the matrix, the float 4x4 matrix at the end of the day to pass on to the renderer. So it's completely independent of the other two systems and says, oh, you have a position, you have a heading, I'm going to make a matrix for you, and I'm going to give it to the renderer. So these are three systems working independently to do just their job very simply and to burn through those component streams as optimally as we can make it by default. So what do systems do? As a general pattern, systems have a few phases that they almost always go through. The first of which is query the component. So a system says, these are the components that I'm interested in, give me the streams back. Then they allocate whatever temporary result buffers they need, if they need any. Then they do the work of declaring the data that you're using and the permissions that you're using on. And then execute, do the thing, do the execution kernel across these component streams. So these are sort of like the basic phases that go through a component system. So let's look specifically in the specific sample, the MoveForwardSystem, which is the simplest system in here, and sort of how it actually works. So first phase, query components. It's specifically querying for a combination of position, speed, rotation, and move forward. In this particular case, it finds no matches. 0 because we're not using rotation, we're using heading. But it also queries for position, speed, heading, and move forward, in which case it finds match. In which case it finds, in this particular example, 25,000 matches or whatever, however many Boyds you have running. Move forward, I'll call out, is we're currently using, is a component, but it's also an empty component. So we're also using components as tags, effectively. So we're saying, does this move component exist on here at all? Therefore, I'm looking for it to match, right? But it doesn't actually have any data on it. Practically speaking, in terms of coding, it looks like this, right? These are our two queries. Query, in this case, you can consider the get component group call. And it's asking for move forward, rotation, move speed, position, as mentioned up there. So I'll notice the sort of declaring your permissions, right? I'm declaring that I'm only wanting to read this particular component. And here we also have the ability to suggest that, to state that I don't want this component. Like if it has a rotation component, even if it has a heading component, then I'm not interested in it in this particular query, right? So we can do subtractive queries as well. So the next stage in the MoveForward system is declaring your data used in permissions. So as we just talked about, it sort of looks like this. Read write for position, read only for heading and speed, and forward is irrelevant because it's just used as a tag. So the execution kernel is pretty much what you'd expect. Like there's no magic here, right? Takes a position, adds it to the heading, times the speed, times the time. Like there's nothing magic going on here. In fact, in code, it looks almost identical to that process. I'm declaring in the job the data that I need, the permissions there, that I'm getting the time, and I'm doing what looks like almost exactly the same as the sort of the pseudocode description of this. So it's this very familiar code, I think, in C# in the ecosystem that we're used to. And yeah, it should remain familiar. All right. One thing that I think is sort of a frequently asked question is, are each one of these execution units, these execution kernel invocations, their own specific job? Like, is this like a million little micro jobs all running? And in fact, it's not true, right? These are all, for us, these are all, this is something that we control. These are all batched up together in the appropriate sizes and lengths. Part of which you can hint on your end from the API, and those loops going over a bunch of these kernels on a particular thread can then be unrolled by the compiler, so you can get sort of maximized performance within that particular batch. Specifically, we have an attribute called compute job optimization, which is the thing that enables our burst compiler. So if you're going to test it, you need to turn it on. I'll also point out in the MoveForward system example specifically that it uses these two attributes, so update after and update before, and these allow you to control system ordering on the main thread. And I'll specifically call out the update after transform input barrier because we have a concept of barriers, which are essentially just, for all intents and purposes, empty systems on the main thread that allow you to create named synchronization points. So I want all of these things done before this point, or alternatively, I don't want to start anything after this point until all of these things are done. And that's largely because if you do, system-to-system dependencies, every system you're sort of trying to draw that diagonally, and I'm trying to say this system has to wait for that system, and this system has to be after that system. At some point, that becomes sort of too complicated for you to manage. So having very high-level barriers that you can manage and that you can name gives you, a much simpler way of managing your frame. And honestly, you want to minimize the synchronization points across the frame anyway. Barriers also give you a point at which we can do what we call entity command buffer flushing. So in order to preserve determinism, changing the component string inside of a job is not inherently a good idea. While those jobs are running, you want to make sure that the component data is stable, and you want determinism to be equivalent to whatever's happening in the jobs, equivalent to whatever if you had done it on the main thread. So if I had done all this stuff on the main thread in just one big long sequential sequence, I should get exactly the same results as if I'm putting it into jobs. So we can guarantee that, but part of guaranteeing that is making sure that this flushing happens at sort of guaranteed points, and that's what barriers do for you. So you can do, like say I want to add components and edit components or whatever into basically into a queue, which then get flushed at the barrier point. And you can declare what barrier that is you're going into. So as I said, add delete components basically happen on the main thread at that point. So that's the MoveForward system, right? That's a simple system. BoldSystem is in concept is very simple, right? It's just changing the heading. In practice, right, how do Boids generally work? If you're not familiar with it, usually it's like, you can imagine a bird or a fish or whatever, and the idea is It's targeting some target or multiple targets, right, moving towards some target. It's trying to avoid some obstacles, and it's trying to avoid bumping into the things next to each other, and it's trying to align to the things next to each other as well. So the common sort of naive approach is this sort of n squared, looking around to all my neighbors, and every neighbor looking around to its neighbors and trying to avoid that. We don't want to do any of that. So it's this is a much more sort of flow-based approach that's divided things into effectively sparse cells so that most of that information can be held in those cells rather than doing this per Boyd, every Boyd, per Boyd kind of operation. So there's some complexity in managing that data, right? So this is why I think this is a good example of even looking through a sort of embarrassingly parallel problem. But the first step of BoldSystem is, again, to query its components. What is it interested in? It's interested in those targets, those things that I want to head toward, right? So it says, give me things that, those components that match both having a target component and those target components that also have a position component. And it finds that. We have some targets running around in the scene. Also give me those components that are obstacle components and with a matching position component. So we have obstacles moving around the scene. In fact, that shark that sort of runs through the fish, right, that they avoid. And give me those component streams that have a Boyd component, a position component, and a heading component, which we have a match for because that's, in fact, all the Boyds running around the scene. So those are the queries, effectively, that the BoldSystem do. And it looks largely the same as the previous example that we had set up. A component group, I say query, but a component group is really just sort of these parallel streams of component data, right? That's what I'm asking for, and that's what we're calling a component group. Sorry. Microsoft update. Cancel. We have an entity debugger as well. Still early days, so we're open to as much feedback as you can on how we can visualize this data much better. But you can see the results of those component group queries here. The matches of heading, position, Boyd would give us 25,000 individual results in our streams. Position target, we have 2 targets running around the scene. Position, Boyd obstacle, we have 1 obstacle running around the scene. So we can look and see what the results are, and we can examine those, and we can examine the properties of those and all the things that you're sort of accustomed to in that way. So as I said, the next stage, declare the data used and your permissions. So we have those 3 particular groups. So to our target group, I'm not interested in the target component. As I said, it's sort of a similar way. It's just used as a tag, so I'm not reading from it. But I am interested in reading the positions of those targets, so read-only positions. Similarly, obstacle group. The Boyd's group, I want to know that I'm reading from the position, I'm reading the value in the Boyd component, but I'm writing to the heading. The point of the system is to write to the heading component. So as I said, those 2 are tags. And at this point, I'll point out the Boyd component itself is a different concept. It's a new concept that we're using in this particular system, which is we call a shared component. And the shared component is really groups of related component data. And those groups are defined by a specific shared value. So in this particular case, all these Boyd components are actually the same value, right? Each one effectively says this is Boyd value A, right? They're by value the same thing. In which case we know because they're declared shared components, they're not stored. They're not stored in a way that's every individual one is copied and stored. They can be combined, and those streams can then be allocated in a way that's relative to that particular group. In practice, basically you say, I want those 3 things, then you filter based on that specific value that you want. And you're left with the streams that match that value. The next stage is allocating whatever temp result buffers that you have. In our case, because we want to do things based on these sparse cells, right, we need to allocate data for those cells. So the important thing here, in this particular problem, we've decided to go with a sparse solution. So the Boyds move around, they move around however distant they want and however far from each other they want, so it's a sort of the sparse grid, right? If you were doing a dense bounded grid of things, that problem would be completely different. You would approach it differently. You may have something like a 3D texture or something like that where you have a sort of a bounded space that you can do it. But because we decided to go with the sparse solution, it's a completely different approach. To go back to the sort of native containers that we're using, in this particular case, we're using 2, native array, which is pretty much what you expect it to be, right? It's a literal array of data. It's a pointer that points to some memory somewhere. And a native multi-hash map. So let's look and see what we allocate here. So these are the two component streams that we have. These are the ones that we're given. These are the native arrays that we allocate. These are basically our cell information. And these are all parallel to our position heading component data. So basically, we're allocating them to be parallel to that position heading component data. We also allocate this hash map. And it's important that the data that we're dealing with is not opaque, right? The important part here is that you can reason about what the data is. So I'll talk a little bit about what the data layout in the hash map looks like, and then we'll talk about why that's important and why that became important in this particular example. So essentially, hash map is this. And our particular hash map is this array of buckets sorted, which is hashes go into the buckets. The hashes themselves can be hashed to go into a smaller set of buckets. It's a very straightforward approach, where you have for each of those buckets, you basically have an array of hashes independent of array of values. So as I said, the data layout for this is important. So let's talk about the execution kernel for a BoldSystem, for this particular BoldSystem. What does it look like? There's a lot of jobs that go into making this work. The first thing is that HashPositions job, which you saw as sort of a main phase in the profile. But we also have a bunch of little smaller jobs to sort of initialize things. We have initialize cell alignment job, initial cell separation job, initial cell count job, copy target position jobs, copy obstacle position job, merge cell job, steer job. So all these are all the things that sort of work together in order to finally write the heading, right? So I'm going to talk about what each of these things do and why. HashPositions job. So we want to declare our data and our permissions. So I'm saying I want to read the positions, I want access to the hash map to write to, and I want the radius, basically the cell radius that I want to deal with. And that's pretty much it. The execution kernel is very, very simple, right? I'm just basically taking the quantized hash of the position and stuffing it into the hash map as the key and assigning as the value the index of this position in the string, right? So this is a very simple execution kernel, and it looks largely like you would expect. There's nothing complicated about that. Here's our permissions, and here's our kernel. I'd also like to point out at this point that we also have a burst compile output inspector. So the code output is not opaque, right? What the compiler is doing here is not opaque. You can see what the compiler is doing. You can see what the assembly looks like. You can see what the LVMIR looks like. So you can reason about what our compiler is doing. So if you see that it's doing something that is not appropriate for your situation, or it's not optimizing the way that you expect, you can talk to us about it, and you can replicate it, and you can, and we can reason about the problem, and you can reason about the problem. This is not about making things more opaque for you. However, you don't have to open this particular window either. Let's get back to the HashPositions job. So high level, let's talk about sort of what we're talking about. So imagine the scenario in which you have this sort of grid, right? You have 4 voids, and you have this grid size represents our cell size that we selected. And imagine it's 2D. You have position A and C, which are relatively close to each other, and so within the distance of our selected grid radius. We have B is often somewhere else, and D that's often somewhere else. So really, the hash of C and the hash of A are the same. When you hash them down, they're in the same grid, right? So what happens? What does our hash table look like at the end of this? Well, what it looks like is that we put into bucket X hash of A and 0, which is the index of position A. We also put hash of A, and, because it's the same as hash of C, and 2, which is the index of position C, right? Those two things go in the same bucket. Hash of B goes into some other arbitrary bucket with the value of 1, because that's the index into position B. And hash of D goes into some other arbitrary bucket with a value of 3, because that's the index of position D, right? So that's what our HashPositions job looks like. What does our initial cell alignment look like? Cell alignment job look like? So this is happening. We haven't set up a barrier. This is happening at the same time as the previous one, as wide as your number of cores and threads are available. And it's pretty straightforward. We have asked to read the headings, and we've asked to be able to write to the cell alignment parallel array that we declared. The execution kernel is very straightforward. It just says copy this and do that. And so you end up with a duplicate of the original array. So in fact, if you want to copy, there's not really a custom job that you need to do that. We have copy component data type here, which just says exactly that. Just copy from this into this other native array and schedule it. Initial cell separation job is the identical thing. We're copying component data from the positions to the cell separation array. Initial cell count, again, at the same time, in parallel to all these things, at the limit of your hardware, we've declared we want to rewrite into the cell count array, and our execution kernel, for all intents and purposes, says just initialize them all to 1, right? So we end up with an array that's all ones. What does that look like? Again, no custom job really is necessary for this. We have what is, I think, obviously named as memset native array, so memset across this particular native array with a particular value. Copy target position jobs, again, happening at the same time at the limit of your hardware, is taking the positions that match the target component and copying them into this target positions, copy target positions array, so it looks the same. It's a copy of those targets. And the reason why we copy, in this particular case, the reason why we copy the target positions, as I said, one of the important things to consider is what we have is design for in-order processing of component streams, right? In this particular case, for any particular cell, I want to arbitrarily index targets, right? A cell the closest target may be 1, or the closest target may be 0, or the closest target may be 3. It's sort of random access for those inside that target array. So that's clearly not linear access into the target array. So in that case, we want to move it into a native array, which is much better designed for random access. While you're doing random access, you're obviously going to take the hit of I'm going to have a cache miss or whatever because this thing is not in cache. However, some things that's simply true. That must happen, right? That you can't get away with not having no cache misses ever. That's not a thing. Like at some point, you do have to load data. This is one of those cases. But the code looks exactly the same as the previous examples. Copy component data. Copy obstacle position jobs is copied for exactly the same reason. We have obstacles. We want to randomly access them from cells. So BoldSystem execute, where are we at, right? We did the hash positions, we've done all of our initialization, now we're to the meat of it. Let's get the cell data down, right? And let's figure out what that looks like. So what does our data look like now? So in our Boyd group of data, we have the positions and headings that we originally queried. We've initialized our cell alignment and cell separation to be basically equivalents of those duplicates. And we've initialized our cell counts to 1. Our hash map, given our simple example, basically looks like this. And our obstacle group, we have a copy of the positions. And our target group, we have a copy of the target positions. So this is what our data looks like now at the sort of state of beginning to build out those cells. So let's talk about what the cell merge job does. Up to this point, all the examples that we've been looking at are almost all exclusively iJob parallel 4 or some variation on that. Go wide, do each thing, individual kernel on one thing, right? But we don't provide you a way to just do custom job execution, right, where you're providing that kernel. We also provide you a way of doing custom job types. And when you understand the data and you understand the data layout, that becomes critically important or valuable. So in this particular case, I created my own custom job type, which I like to call iJob native multi-hash map merge shared key indices. I'm open to alternative names, but that's mine. So what does a custom job type allow us to do? The first thing is it allows us to build, and most importantly, it allows us to build custom safety rules, right? In this particular case, when I'm accessing a hash map, I have very particular rules based on the data of what's allowed to be written and read from various threads. So I can define those rules, and so anyone who ever uses this can now be guaranteed that that use is safe. And they can guarantee that there are, in fact, no race conditions when they use it. So they can be very confident when they use it. And that's because we know how hash map storage works, and we can iterate safely in parallel. So again, let's talk a little bit more about iJob native multi-hash map merge shared key indices. I had to shrink the font a little bit to get that to fit. So imagine you have a hash map, right? Let's just take an arbitrary example. So in your hash map, you have, again, remember we have sort of parallel arrays of hashes and values. You have hashes. You have the letter A, which represents some hash, the letter B that represents some hash, and values that are associated with them. So how do those go into buckets? So you can imagine that as I'm sort of putting those values into buckets, A with index of 0 from the top goes into the first bucket. B with index of 1 goes into the second bucket. The second A with index of 2 goes in the same first bucket because it's the same hash, etc. For A and B. C, which is in some entirely different bucket, goes with the index of 3. And D, because we see it twice, and of course it's the same hash, goes in the same bucket. So this is, in this sort of arbitrary simplified example, that's sort of what the layout would look like. But what this means is, if we iterate each bucket in a separate thread, we can make certain guarantees. Everything with the same key will always be in the same thread. And anything that refers to a hash, or the same hash, will also be in the same thread. So we can make certain guarantees if we iterate each bucket independently in different threads. And that's what we take advantage of in this particular custom job type. Anything with the same hash will be in the same thread. So what this particular custom job type offers is 2 execution kernels. One is execute first, so the first time I see this particular hash, and the second is execute next, so any subsequent time I see this particular hash. And it passes the index, or in this case, the value that you stored in the hash with you. So the first value, when the first encounter, and when any subsequent, it tells you the value of the first value and then your current value, which we use as an index in this case. So what does that look like in terms of transformation? In our example hash map, it basically looks like this. So remember our example hash map. And so execute first in some thread X, right? We execute first. We're given 0, which is that index stored with A. We're given 1, which is that index stored with B. We're given 0 and 2, which corresponds to the first time we saw A, and this current time we see A. 0 and 4, which is the first time we saw A, and this current time we see A. 1 and 6, the first time we saw B, and this time we see B, right? And go so forth on the other threads in the other buckets. So, reminder, this is our simplified Boyd example. What does that look like in this scenario? So we have on some thread X, which represents that sort of A and C group, we have execute first 0, which represents position A at index 0, and we have execute next 0, 2, which says the first thing you saw was A at index 0, and the current one is C at index 2, right? And similarly with hash B and hash D, and they're separate threads. So let's look at sort of the process that's happening in execute first here in this sort of particular job execution kernel for this particular Boyd's example. Like, what are these things actually doing? So in the execute first case, the things that we want to do, so the 3 cases of execute first are A, B, and D in this particular case. So the thing that corresponding to these places in the hash map. So the thing that we want to do is find the index of the nearest target. You know, what's the thing that I want to target for this particular cell? What's the obstacle for this particular cell that I want to avoid? What's the distance to that obstacle? And what's the index of this particular cell? That's it. That's what I want to track in the first execution. So what does our data look like at the end of that sort of execute first pass? Our obstacle and target groups don't change because we're just reading from those. We're trying to find those indexes. So if you remember, we're only going to be, execute first only applies to the 0, 1, and 3 cases in our simplified example. So we're writing the cell indices, which correspond to those indices, 0, 1, and 3. We're saying the closest obstacle position index is 0, so the first obstacle for each one of these cells. Here's some arbitrary distances from those obstacles. The nearest target may be different for each cell, like a 0 target, a 1 target, or whatever, it's arbitrary. And the cell count hasn't changed. So in code, this is what it looks like. Right here, we're declaring our data and read-write permissions here. And the code itself for the execute first kernel is, again, should feel fairly familiar, right? We have the execute first kernel. It does the sort of naive approach of what you'd expect. Find the nearest position for given these obstacle positions. Return me the index and the distance. And the nearest position is sort of the same sort of naive loop that you would expect, right? Target position is the same thing. And it writes out the cell index here. So this is a very straightforward, sort of familiar approach, I think, that we're not introducing magic. So let's look at what the execute next kernel does in our particular example of the Boyds. So the idea is it comes in, and that's for this particular case, right? The second instance of hash A here. So it sums the positions in the headings. It sums the counts of all the voids in the cell, because I need to know how many neighbors do I have in the cell, right? And it gives me an index of where those sums are stored. So what does that look like? So 2, in our example case here, is what is the index that we're dealing with. This is the second case. And so this is where, because we have control of the job, and because we can control the safety and what thread things are running on, that we can guarantee certain things. So 2 writes its index, the sums will be stored in index 0. But it can also write into index 0, that first index, because we can guarantee that because they share a hash, they're running on the same thread, there is no race condition, we can guarantee that this write is OK. So it sums the heading for C and the position of C into that value in that particular cell. And increments the cell count. So now you know there's 2 neighbors, and there are the sums right there. Execute next kernel in code is very straightforward and simple. It's sort of exactly what you'd expect. It increments the cell count. It sums the alignment and separation, so that position and heading values that we stored, and stores the index of the first value where we're storing the cells. So where are we at in our void system? We've done all the initialization, we've hashed positions, we merged the cell jobs. Now we we have all the data we need. Now we just do the steering part. Like let's get those voids actually pointing in the right direction. So what have we written? We have summed values, right? We have the summed values for a particular cell that happens to have more than one void, and for any subsequent position, it points back to that data, right? So everybody can point to the right sums. So it points back to 0 in this case. Effectively, this is what the kernel looks like. It's like, do some steering stuff with all this data and put my heading in here, right? You have all the data in place. The point of this whole system is to write heading out. This is actually what the job looks like. But it's less daunting than it seems in this sort of block of text. We've declared our data and read-write permissions, and notice almost everything is read-only except for the headings, right? That's the thing that we're writing here. This block is just we're reading a bunch of individual values out of these things, mostly because these lines would be out of control long if I didn't put them into separate variables here, right? But this is the actual block. This is the bit that's doing the steering and sort of the way you would expect to do steering, right? There's nothing magic about it. There's nothing even that interesting about it, but that's sort of what it's doing. And then finally, it just stores the heading at the end of the result. So let's look at sort of all the components that we have in our system. We've talked about position and heading, and move forward, and speed, and voids. We've sort of talked about all those, but what we haven't talked about yet is the matrix, right? We know we have the position, we know we have the heading, but how do we build that final matrix for the render system? The transform system is the thing that handles that. In particular, in this example, it does that query for heading, position, and matrix, right? Do you have those 3 things? That's a match. It also searches for, do you have a TransformParent? So for hierarchical transformations. In our particular case, there's no match for that. And that's because these are basically all world space routes running around the world, right? So you have a bunch of things in world space doing nothing. There's no hierarchy. So we can customize for the specific case of, I just have a bunch of stuff in world space. And in fact, we can customize for that particular transformation. So we have a job, update heading, transform no hierarchy routes. That specializes on that particular transformation. Given read-only positions, read-only headings, read-write matrices, it does the thing, the sort of naive thing that you would expect it to do. I have a position, I have a heading, I picked an arbitrary up, Y up, and stuff a matrix in there. So nothing at all special or magic about this transformation. And in fact, the execution kernel looks pretty much exactly like that. So that's how voids work. Like there's no magic about what we're talking about. What we're talking about is getting all those clowns out of the car, right? What we're talking about is stop doing all the stuff that gets in the way of the work that we're trying to accomplish. Simplify it, do it, and as close to an optimal way as possible. Give you the tools to do that by default, and things become simpler and easier and faster and much more straightforward to reason about, both from our point of view in terms of compiling it and your point of view in terms of putting it in. So we don't do any more. I mean, the takeaways here is we don't do any more than is required by the actual data to solve the problem. Like, this is the data, this is what we need to do, that's what we do, that's it. We don't do anything else. It's based on straightforward, simple data transformations. And I'll remind you, entity is not a container. In no way, we talked about how the voids work. At no point in there did we talk about entities. Like, entity is not a requirement to reasoning about how those transformations worked, right? So where does an entity come into play? It comes into play in 3 cases. One is if you want to add a set of components with a common ID. That common ID is an entity ID. If you want to delete a set of components with a common ID, that ID is an entity ID. Or if you want to reference a separate set of components in a component stream with an ID, that ID is an entity ID. Those are the 3 cases of using an entity. So let's talk about actual use of those cases, and that would be a hierarchy, right? If I'm doing a transformation hierarchy, I obviously need things to reference each other in some way across streams. We have an example that you can download and look at called a hierarchy example. Visually spectacular, as you can see. The idea, though, is you can see a bunch of things in sort of a local space, transforming in a local space that then gets transformed by hierarchy, and you can see how that transformation actually works. So that's all done by the transform system. The transformation system is basically set up into phases. First phase is it transforms all the root matrices in parallel. Like, find all the roots of the world, transform them all once in parallel, so now we're set up for whatever hierarchies are underneath that. Then we create a per hierarchy, so for each one of those roots, we create a DAG for each one of those root matrices, should they have a hierarchy. And then we transform each hierarchy in parallel to the limit of your hardware. So it's a very straightforward transformation process. So how is that transformation relationship defined? From your point of view, how do I say this position should be relative to this other position, right? Again, simple data, simple, straightforward components. We're using the entity ID here, TransformParent. Just this guy, the entity ID associated with this other position is my parent transformation. And that's it. That's how you associate and create hierarchies. So as a reminder, an entity is not a container. It's simply an ID. So an entity is an ID, in fact, an index into a component stream that allows for quick lookup into a specific component system. That's what an entity is. So talking through a more concrete example, as I said, does it in phases, right? So imagine you have a hierarchy that looks something like this, right? Simplified hierarchy. What happens first? So the first thing we do is to transform all the root matrices. The root matrices in this particular case are A, D, and G, right? And we know that because they, in fact, have no transform parent. So by definition, they are roots. So we transform all the roots in parallel. And we saw all this work because it's basically the same effective transformation that we saw in the BoldSystem. So let's go on to the next phase, which is creating a hierarchy per hierarchy DAG. What does that look like? So we have a job called build hierarchy. And it has 2 requests, 2 pieces of data, read only. One is that parent component with the parent entity ID in it, and the entity ID of the transform parent component itself. And for all intents and purposes, we also have a hash map. For all intents and purposes, all we're doing here is reversing the hierarchy, right? So for every parent transformation component, we basically have a hash list of what all the children entity IDs are. So we've just taken your transform parent component and reversed the hierarchy down from the root. So given that we've done that in parallel, right, for every root in a very straightforward way, we can now transform, starting at the roots, transform every one of your hierarchies in parallel. And we can do that because the entity is essentially just an ID, we can specialize in our component streams with this thing we call component data from entity, right? You can use the entity as basically an index lookup into a component stream. So in this particular case, I'm declaring that I want this data, local rotations, local positions, rotations, positions, matrices. I want to be able to look up this stuff by entity ID as opposed to incrementing index. And the actual transformation tree, you can look at the code right now, is a relatively naive implementation, right? It's a sort of recursive from the root transformation of the hierarchy in exactly the normal way that you would expect it to happen. We're doing research into much better layouts for hierarchy transformations in particular because we know that's sort of crucial performance area. But the point is that we are at a state, because we've set the data is in a very straightforward layout, it's optimizable, right? We're at a place where we can take that and we can optimize it, we can move it forward, we can do things with it. We don't have to throw it all away and start over, right? And just, at the end of a project, that's not something you're going to have to do. That's the idea. I say that, but we're still preview, and these things might all change, right? The specific components that we're using right now. We also currently manage all the component combinations. So I just put a position component in. Okay, fine. Like we'll figure out, we'll assume that what you want is, an identity rotation. We'll put that in. I just put a heading in and no rotation. So I'll build the matrix out of just the heading. Or you put a heading and a rotation. We'll assume that you're going to build the rotation with the heading. So we'll ignore the heading and we'll build the matrix with the rotation. So we sort of mix and match whatever combination you throw in there. We're trying to create the appropriate matrix, which you can overload, of course, and you can say, I'm going to build my own transformation system that does the custom thing for me. But we try to make this, you put something in, you're assuming something will come out, and we try to make it as straightforward as possible. And again, it's all being transformed in parallel per hierarchy at the limit of your particular piece of hardware. And this is a reasonable and optimizable default. And this is what we want to see across the board for everything, for game code, for engine systems, for everything. And we're working in the same system that you're going to be working in to demonstrate how that's possible. We're building engine code in C#, right? So that we can demonstrate how this is going to work and how it's possible. And we're giving an early preview into that experience so you can help us sort of guide that process. So in conclusion, it's not magic, right? Nothing here we're talking about is really magic. It's based on simple engineering, simple practices, understanding what the data is, knowing that we have more context about that data so that we can take advantage of it. We can give that data to the compiler. We can make that accessible to you in a very straightforward way that gives you performance by default on the order of 2 orders of magnitude above what you're used to now when you're using C# scripts, right? And potentially even further beyond that. So it's good performance. By default, it's optimizable by default. So you can visit our forums and download what we have already here. And I'm open for the next few minutes for any questions.
So I'm trying to envision what the use cases of this would be for common game subsystems. You gave the Boyd's example, but what about, the things you would usually build in a game? What kind of systems would you consider using this for?
Well, I think without being trite, I think the real answer is literally everything. But to make it more concrete, has anyone ever had a problem with, say, UI performance in your game? All right. Here's part of how I define data-oriented programming, right? Data-oriented programming should the actual global energy that you use to make a transformation should be proportional to the amount of surprise in the data. So when you look at a UI, when you look at it frame to frame, right? For any given UI anywhere, the statistical chance that frame B is identical to frame A is extremely high, right? So the actual transformation cost for that should, in reality, be very low. In practice, for most people, most of the time it's not. It's actually ridiculously high, not just in Unity, but across the board in the industry, right? That UIs tend to have a relatively high cost, frame to frame. That's the thing we want to fix. So in fact, UI, in particular, is a very good match to what we're doing. You can imagine the same sort of layout, component layout with a UI. But also things like bot code, right? Game code, the actual things. Like you can imagine those, and there's a lot of, I think, a lot of experience out in the wild of sort of using kind of entity component systems for AI systems, right? For state machines or for whatever. So, really, from our point of view, the answer is literally everything. Like, whatever system you're thinking about can actually benefit strongly from having adhering to very strict rules that we can optimize for, and for having very clean data layouts.
Yeah, I think that's true, but it's also true that just using a traditional game object system would be simpler.
I don't actually agree with the simplicity question. I know it's more familiar. And I think that is a thing that we need to address, right? I think the familiarity of what you've done and what everyone has done for a long time, and many decades of teaching is something that we absolutely are addressing, right? We need to meet people where they are and help show you how to get from there to here. But at the end of the day, like once you've gone beyond that hurdle, I don't agree that it's in fact simpler. I think what we're talking about is simpler ultimately because what we've done is removed things other than the thing that actually solves the problem. So everything else that you've invented to put into it, all this extra complexity, that's all just gone. That doesn't exist. So ultimately, it's in fact simpler. But you should experiment. You should sit down with it. You should show us where you believe that this is in fact simpler than this. A is in fact simpler than B. Show us that. Sit that down, right? And we can talk about, either why we disagree in this particular case, or we can improve what we're doing.
Thanks.
Two quick questions about just sort of the specifics of the example that you went through. So you didn't actually mention any barriers in that first example. I guess when you did the merge cells, that would have been a barrier.
Right. There's a transform system barrier. Basically, is the only real barrier in the system. Right. So you want to make sure that you update your positions. Well, in this particular case, I'm updating my headings before any of the transform system is working, right? I want to schedule it. You saw in our original schedule that sort of I had all those sort of BoldSystems running before MoveForward and before TransformSystem. That's because there's a barrier before that MoveForward, so that, that all that stuff is done before the transform system ran, so that you don't have an extra frame of latency for your final matrix transform, right? If you want an extra frame of latency, right, you want a double buffer or whatever, you can do that. But in this case, we want as low latency as possible. We want that 60 frames and that to be this frame.
Right. You also did some queries where you in one of the resulting components, you had no read or write access. What was the point of that?
That's because the particular component was empty. It was just simply used as a tag.
Oh, okay.
So it's used for, so that I know that these are related things, right? I'm looking for all the targets. I'm looking for all the obstacles. The fact that they have the component in them is simply the tag that I'm using to say I want that stream of component data.
Okay, and then in terms of how this can be applied generally, so how useful do you think any of this will be on mobile?
I think it's extremely useful. In fact, I think critical for future mobile performance. I think power consumption on mobile is a huge issue. And one of the things that, aside from looking for that top end, the top end performance on mobile, it's also that regular performance, right? What you don't want to do is overheat the device for a relatively simple game, right? What you want to be able to do is say, look, this game only really requires 2 milliseconds or 4 milliseconds or whatever for a 60 millisecond frame. So I'm going to do all that, go wide, really quick at the beginning of the frame, and then let the CPU rest for the rest of the frame. So then basically you can get sustained performance over a long period of time instead of overheating the device. So critically important for mobile applications.
Okay. And then finally, so I asked this in the jobs talk yesterday. I'm really interested in applying this to the physics system, but it's not totally clear right now how that would work until the physics system itself is, I guess, Java-fied or whatever. So is there a way to start using this right now with 2018.1 to improve physics?
So, the question is really about physics and how physics integrates with what we're talking about. I'd say, what Joachim talked about is the sort of future of determinism, right? And so that implies that we also need physics, deterministic physics, which you can take away whatever implication you want from that, but we need to do serious work in this area. As of today, we don't have that answer, right? That's not in place, that's not in the system. This is a very early preview with just the basics in here. However, if your needs are relatively small, right? You're doing a relatively simple game and you want to do some, relatively self-contained raycasts and things that you can do simply that don't require a full physics system, right? That's something that you can put in place now, right?
Okay, yeah, thanks.
All right. All right, thank you.